Okay, all right. So let us look into example 8.7. Okay, so which will cover problem solving on single slit. Okay, so for this one, example 8.7, you have a sodium light. Okay, so wavelength over here given 580 nanometer, shines through a slit and produce a diffraction pattern on a screen 6 meter away. Okay, so this will be the distance from the source to the screen. Okay, and then the width of the central maximum fringe of the screen is given lah. Okay, so this is the width of the central maximum. Okay, so based on this information given, they want you to determine the width of the slit. Okay, and then B, angular width of the central maximum fringe, and then C, the number of minimum that can be observed on the screen. Okay, so for first question, okay, so what we do is that we list out all the information given. Okay, lambda given, okay, capital D, distance from the source to the screen, okay, and then the width, okay, of the central maximum given. Okay, so if you draw the situation, we will end up something like this lah. Okay, so this will be your width of the slit, your A. Okay, and then this will be the width of the central maximum lah. Okay, so basically the width of the central maximum will cover from first minimum, okay, up to first minimum over here. Okay, so that means whenever we have central maximum, okay, whenever we do calculation, the calculation will always end up with minimum. Okay, so that means the brightness will end over here at the first minimum over here. Okay, now we can apply the equation. Okay, so width, which will be equivalent to twice the value of y distance lah. Okay, so the distance over here. So let's say this is distance y1. Okay, y1 for the first order lah, and then this one also will be the distance for y1 for the first order for above and below lah. Okay, so this is, let's say this is your reference point. Okay, so this distance will be y1 lah. Okay, for first order. So the same goes over here lah, y1. So the total distance will be w. Okay, okay, so from the equation, okay, to determine the value of y, okay, so since it is width, okay, so the distance will become twice the value lah, twice the value of the y. Okay, so rearrange, we can find the value of a over here. Okay, either you do it like this, or what you can do is you just simply can divide the width lah. Okay, divide the width, you determine the value of y. Okay, for first order. So once you have the value of y, just replace it over here lah, no need to multiply by 2 lah. Okay, so you will obtain the value of the width. Okay, okay, now to determine the angle. Okay, so basically for the angle, okay, one method, you already have the value of the d and y. Okay, so basically we can calculate from there lah, or what you can do is that you can apply the equation. Okay, so applying the equation, okay, width equivalent to times the value of theta, okay, where theta will be the ratio of lambda over a. Okay, so we already determined this. Okay, just replace in and find the final value lah. Okay, so for the angle, it will be twice the value lah. So because over here theta 1, it either refer to 1 point only lah. Okay, so twice the value, which will end up with 4.78. Okay, and then C, okay, C, they wanted to determine the number of minimum that can be observed on the screen. Okay, so for problem solving, okay, we look into the equation first lah. Okay, so this is the equation that we can use to obtain the number of minimum. Okay, so whenever they wanted to calculate the amount of maximum fringes that we can observe, okay, so the possibility of the angle over here will become as 90 lah. Okay, so maximum order, so the angle will become as 90. So this is the furthest it can refract away from the central bright lah. Okay, so after this you won't have any pattern observed. Okay, so this will be the highest angle that you can observe lah. Okay, so replacing over here. Okay, so we are going to determine the number of order, so maximum order, how many n that we can obtain. Okay, so calculate. Okay, now the maximum number of order, okay, fringe that we have is 23.97. Okay, so that means it only can form order up to order 23 only. Okay, you don't round it off and make it as 24. Okay, so the order will become 23 only. So this order is for one side only. So whenever we are doing calculation, we will refer to one side. So let's say on top over here, as the angle goes, it can form order up to 23 order for the top portion. Okay, so that means for below, bottom also, it can form order up to 23. So that means the total number of fringes can be up to, okay, you will have 46 lah. Okay, multiply by 2. Okay, because 23 for above and 23 for below. Okay. Alright, next we look into example 8.8. Okay, so this one they wanted to state the similarity and difference of double slit interference, okay, and single slit interference pattern. Okay, similarities and the difference. Okay, and then B, how many bright fringes will be produced on a screen. Okay, if you have a green light wavelength given 553 nanometer, okay, and then the slit width is given as 8 micrometer lah. Okay. Okay, now for the first part, okay, similarity. Okay, so the similarity is that both pattern consists of alternating dark and bright fringes. Okay, so that means you will observe fringe pattern lah. Okay, bright and dark. Okay, second one, central for both pattern is bright fringe. Okay, so the central you will end up with a bright fringe lah. Okay, and for the differences. Okay, so for the single slit pattern, okay, the width of each fringe, okay, you will end up with the same width. Okay, so for single slit pattern, the central fringe will be wider lah, compared to the other fringes. And for double slit, intensity of bright reduce slowly, okay, as the distance increase from the central bright. Whereas for single slit, okay, the intensity of the bright fringes reduce rapidly, okay, as the distance increase from the central bright. Okay, alright. So next for question B, okay, we are given with value of wavelength and the width of the slit. Okay. Okay. So this one they ask you to determine the maximum, right? Okay, so therefore we need to use the equation for bright fringes lah. Okay, bright fringes A sin theta should be equivalent to n plus half lambda. Okay, so for the maximum bright, okay, so the condition will be still same. Okay, so the amount of maximum will be formed when the angle becomes 90 lah. So this is the maximum possible angle that we can observe. Okay, so replace in all the given information. A already given, so sin 90. Okay, number of order maximum. Okay, so over here we end up with 13.97. Okay, so 13.97, that means maximum order will be 13 only. Okay, so which will end up with 13. So the total order will become, okay, so same like the previous one, we multiply by 2. Okay, 26, and we have plus 1 over here. Okay, so this plus 1 refer to the central bright, because whenever we do calculation, we take it as a central bright as a reference. Okay, so reference we don't include in the calculation. So this one refers to central bright. Okay, so total we will end up with 27 fringes. Okay. Okay, so for example 8.9, okay, it's on last subtopics lah. Okay, so which will be discussing about diffraction grating. Okay, so this one example 8.9. Okay, you have a monochromatic light, okay, unknown wavelength, okay, falls normally on a diffraction grating, and then the diffraction grating has 3000 lines per cm. Okay, and then if the angular separation between the first order maxima is 35, okay, angular separation between the first order, okay, that means between two first order lah. Okay, so they want you to calculate the wavelength of the light and then angular separation between the second order and third order. Okay, now for this one, given information, okay, capital N, okay, number of line per unit length, the width means the angle from first to first order, okay, so the order will be 1 lah. Okay, so if we draw what, we will end up some sort like this lah. Okay, first order, so the total angle is 35. Okay, so from this we can calculate the angle for one first order lah. Okay, so based on the drawing, okay, total 35. Okay, so for one order will be 17.5. Okay, and then we can calculate the slit separation, which will be D, okay, which is equivalent to 1 over N. Okay, so where we will end up with, okay, convert into SI unit lah. Okay, so which will end up with 3.33 times 10 to the power of -6 meter. Okay, so once you have all the information sorted out, okay, you can replace into the formula where d sin theta will be equivalent to n lambda. So over here the n order will be 1 lah. Okay, so d already given, okay, theta 1 because we are referring to order 1, n is equivalent to 1. Okay, so angle we already determined over here, so just replace in. So final answer we will end up with lambda, okay, 1 times 10 to the power of -6 meter lah. Okay, micrometer. Okay, now for situation B. Okay, so if we draw for reference, okay, so n0 order, so which will be a maximum lah, central maximum. Okay, now if we calculate from the equation, we will end up with theta 2. Okay, so the theta 2 will be the angle from the 0 order up to second order. Okay, and then theta 3 will be the angle between 0 to third order. Okay, because they wanted to calculate the separation between second and third order, right? So we need to calculate angle for theta 2, okay, and theta 3. So once we minus these two, we will end up with the difference lah. Okay, so that means the angle from 2 to 3. Okay, so for this one, just replace in the value, okay, according to the order. Okay, so if we replace for the second order, okay, so we end up with angle 36.9. Okay, and then redo again for third order where n will be equivalent to 3. Okay, to find the value of theta 3, so we end up with 64.3. Okay, so now in order to determine the angle between 2 and 3, find the difference lah. Okay, angular separation. Okay, so 3 minus with 2, okay, so which you end up with 27.4 degrees. Okay, so this is the angle of separation between order 2 and 3 lah. Okay, okay, 8.10. Okay, the last example. The second order maximum produced by a diffraction grating with 560 lines per centimeter, okay, is at an angle of 3.1 degrees. Okay, so now over here they wanted to calculate the wavelength, okay, of the light that illuminate the grating and then determine the number of maximum that can be observed on a screen, and then state and give reason why would you expect to observe what do you expect to observe if a grating with larger number of line per centimeter is used? So this one just explained based on the equation lah, okay, based on the relationship. Alright, so we go into problem solving A first, okay. So we already have a number of line per unit centimeter, okay, so convert into per unit meter lah to make calculation easier, okay. Angle theta 2 for order 2, okay, so just we can replace in the given information to determine the value of lambda lah over here, okay. So since the value of n given, we can substitute to replace the value of d lah over here, okay. So replace in, which will end up with this, okay. Therefore lambda will be equivalent to 4.83 lah, okay, times 10 to the power of -7 meter. Okay, so for number of maximum, okay, same condition like the previous one, okay, angle should be equivalent to 90 lah, okay. So the maximum angle which will be equivalent to 90, so replace in, okay, so which will end up with 36.97, so the order will become 36 only, okay, 36 order. So this one for one side, so for both sides, that means multiply by 2 and plus 1, where this one will be the central, okay. So whenever we have calculation, central will become a reference, so you have to include central lah, okay. For this one applies only for bright, okay, so for the bright fringes, okay. And then C, the fringes will become further to each other lah, okay. So this one we can refer back to the equation, okay. So basically sin theta are inversely proportional with d lah, okay, and will be directly proportional with n, okay. So number of lines per centimeter results in a larger diffraction angle, okay. So that means n increase, sin theta will increase lah, okay. So therefore the distance of separation will increase, okay. So that's all for this chapter, okay. Have a nice day. So chapter 9 will be on quantization of light.